Now let's explain this. Whatever we are doing, if we would write the functions, simple functions, that will be very easy. Now what I can do, how it can be simplified, that I'll tell you with functions. Suppose I have the same list. Now each cases we have seen. What I'll do, see my function. See, in this given element, first may be changed. So I am assuming first as local variable always. So I want to write this way. See, my function returns first node's address because it may change first node's address. Then I'll say delete element is function. What I have to pass? List I have to pass. So struct node star start I am passing. Assume that I am passing element to be deleted also. Element to be deleted. Element. Now when you are writing element to, you are passing, means who should read this element? The caller should read the element and send that to function whenever it calls. Now what cases we are seeing? See, first of all, first case, what is that? If this start, whatever you are sending, linked list you are sending, that is null, it is returning first node's address. If null, can you delete? No. After this also it will be empty list only. In print list it can be handled. So what you can write? Return null. Directly you can write that, because we cannot do anything. Or else you can say empty list and return null. From here itself it will go. This case is handled. If this is not the case, if, what is the second case we have seen? List contains only one node and that element to be deleted is in that first node. What way we have checked that? If first info, this starts info is equal to element to be deleted and start link, if it contains only one node, link is null, right? Now what this case is, one node and that node contains information, right? So you can apply that deletion of that node itself, you can call delete begin also here, delete begin also here, because beginning node, one node that we have already tackled in that particular function also. So you can write here directly delete begin. What it returns actually? Null. So either you can write directly here what we are doing. If this is the case, we are freeing that start, free that start node, and start you are anyway, see, after deleting you have freed, start will be null. So if you return directly null also, there is no problem after this. But if you want it to be clear, set it as null and then you can say return this start. For clarity's sake I am writing this, otherwise return null also will do in this case. If this is not the case, what is not the case? Else if start info is not equal to element and list contains only one element, explicitly you have to write that. Else if opposite condition of this, starts info not equal to element and start link is equal to null, only one node present but the element to be deleted is not there. So what you have to do is return start, because element to be there deleted is not there, and whatever list, we cannot delete anything. Return start means the same list will be there, you may write here element not present, return start. So these cases we have handled. Now how to use different functions, that I'll wipe out this much. Whatever I am writing after this we'll check what, see, else if this case, from here it will return. If this is false, control comes here. If this is false, control comes here. If this is false, control comes out of this control structure, right? Then where control goes out of this means here somewhere. Now list has more than one nodes and you are deleting. In that case, what we have to do, if the element to be deleted is in first node, if start info contains the element to be deleted. Now when this will be checked, when linked list has more than one nodes. Now what you have done, that whatever you have done logic, what you can directly free this start, but first cannot be changed. So first temporary is taken, temporary, it is given start value, then start is moved, start is given start link, or else here directly what you can do, directly you can call delete beginning, del big, whatever you have written, how you have written, accordingly you have to pass this, that's it. So you can reuse this, whatever functions you have written earlier. If start info is equal to element, delete beginning start. Even you can access here also, this delete beginning you can call here also, there is no problem. If this is the case, if element is not, I'll wipe out this. Now else part, for this else part I will write, for this else part. So what will be else part? See, else, what does it mean? The element to be deleted is not first in the linked list which has more than one nodes. So whatever you have to traverse down. Now in this case, now what I will do, what way I can write here, I'll write, see, find element function, and I'll pass that element. What find element should do is, find element should give me whether element is there or not. If it is there, it should give me address of that particular node. If suppose I want to delete 30 will be passed here, 30 will be passed here. So what it show, is it 30? No. Is it 30? No. Is it 30? Yes. Temp stops here. So this temp, whatever stops here, it should return me that particular value. So I'll take element address. You have to delete all, you have to give all these declarations, struct node star element address. So I am getting the element's address by this find element. Why we are finding the element? Sometimes element may not be there, so you can check that conditions also. If it returns me some address, then I can say that element is present. But if find element you are giving as 50, suppose 50, is it 50? It will check, no, list is exhausted. So it should return me null in that case. Means when search is successful, when element address has some value. If it has null value, then element is not found. So what I can check, if element address is equal to ADDR, suppose null, what does it mean? The element is not there. We can say printf no element, whatever you are deleting, that element is not there, and from here itself you can return directly. Return. Now you have to send something, because you are returning something, right? This, which is this case? This case is the list has more elements. So from here you can say return start. Else what conditions will be there? Find element has found the element. Suppose you are deleting 30, so you are getting address of 30 in element address definitely. Now I have to get predecessor node's address. Predecessor node's address is compulsory. So what I will do, see, if element is found, control comes to else part of this, right? If element is found, then what I will do, I will get predecessor node's address. So what I will do, this elements pred address, I'll give find pred of what? The location, whatever you are passing. This is element address. What this function will do now? This will take one value, element address. Suppose element address is this. This nodes what is predecessor. That predecessor I'll take into predecessor address. By this I am getting the predecessor address definitely. Now you have tackled all the cases, first node also. So always for all the elements whatever you want to delete now, for 20, 30, 40, control comes here, and for every node definitely it will have some predecessor node's address. For deletion of 20, predecessor is this. For deletion of 30, predecessor is this. For deletion of 40, predecessor is this. For deletion of 50 is not found. From here itself it will go return to caller. Directly it will return from here itself, right? So here definitely you will get predecessor node's address, because we have confirmed that element is present and the element to be deleted is in this list and it has predecessor. This will never find element. Now find element may return the first node's address also, but first node's element is present in first node or not, that we have tackled already, right? So this case, whatever find element, this will find definitely second, third, fourth, or it will not give you first element. That is for definite, because before this only you have tackled. So how you are writing, it depends. There are many ways. This is one way of writing. So you are getting predecessor node's address somewhere. Now once you have predecessor node's address, this predecessor might be this, might be this, might be this. In this case, this or this. Now what the adjustments only? Suppose this is this element's predecessor address, EPA. I'll shortly write this. Which node you are deleting? This 30. So how you are tackling this? This node temporarily, this node's address you are storing in some temporary. Suppose node to be deleted is elements pred address. Its link you are giving. This link points to this. Otherwise you have this address in element address also. So this is also not needed actually. This is this storage. Directly you have that element's address in element address. So this is also not required here, because if element is there, you will have element's address. That is for definite. So for deletion, so this has element address. It is pointing. This is giving you this element's predecessor address. Now you have everything. Now you have to change this pointer, should point to here. This node you are changing, this field you are changing. How to access that field? Now after this block will start. Elements predecessor address, whatever it is pointing its link field I am setting, and it is given this node's address. Where is this node's address? Link field of element address. In link field of element address you have that. That's it. This will be set. This will be set now. This pointer won't be there. Now one pointer you have set. Now you have to free this node. What is pointed to this node? Which pointer is pointing? Element address. So I'll say free element address. That's it. Now this will be simple. Now whatever logic for find element that we will write. Now what will be signature of find element? It is taking element. What is type of element? Integer, right? Find element. Now which list it is finding? So you have to send list also. In start this element you are searching, two parameters you have to give. This start and this element address. Now what will be signatures that we will see? Find element in this linked list, this element. Start is struct node pointer. Element is integer. In this list, find element and return that element's address. What will be signature of this? Find predecessor. Which list? Then which node's predecessor you are finding? Which node's predecessor? So struct node star, both are struct node star pointer variables, and it is returning struct node star. It is also returning struct node star. That's it. This else part, whatever you are writing is over, and it will do everything. It returns what? First node's address. When it comes inside this else part, definitely it is not deleting this first node. So when it is not deleting first node, first won't be changed. You are deleting either 20, 30, 40 or whatever followed, not first node. So there is no need of returning after this else block. Return start is not required. Before only you have changed, so you have returned from there itself. That's it. If you complete this, you can close this way. So this is a way you can write. Now what way you have to write find element, what way you have to write find predecessor, that you can think and write that particular functions. It is very easy. Find element I want to write. Find element. I'll give only one example of find element. How find element will do? See, this signature, we will write this signature first, and then I'll explain you how to write this. What it is returning? Struct node star, right? Then name of the function is find element, and what you are passing? The list from which you are deleting struct node star start, and integer element you are finding in that. Now what way I can write C? What I'll do is very simple. In this case also, all cases you have to check. If linked list is empty, if start is empty, what you have to return null directly, because the element is, when element is not there in the list, we are returning null, right? Else if it is not empty, then you have to traverse, take some temporary variable. So one temporary variable I'll declare struct node star tmp. Then I'll say tmp is given first node's address, or here it is start. First is pointing to start node. Now you have to check, is it the node to be deleted, element to be deleted or found? Suppose you are finding 30, suppose. Is it 30? It will check. No, if information field of temp is not equal to the element to be searched, then it should be moved. So what, when you are moving, while temp's info field is not equal to element, when this is case, temp is moved to temp's link. That's it. When you this is completed, this I want to write, this is completed. When this is completed, this loop, you will get temp either set or not. But sometimes what happens, if you give this condition only and you are searching for 50, what will happen? Temp's info not 50, not 50, not 50, not 50. When you move again, it will give segmentation fault. So always whenever you are traversing, you should check if temp is not equal to null and temp info is not equal to the element to be searched, then temp is moved. Now every case there won't be any segmentation fault. Now what is happening, see, if you are searching for 10, what will happen? Temp is here, temp is given start. Whether temp is null? No. Temp's info is equal to, if 10 you are searching, is temp's info is not equal to element, this is false. This is false. When this is false, it will come out, means temp is pointing to the node which we want, right? If you are searching for suppose 30, what will happen? Temp is given start. Temp not equal to null? Yes, true. Temp's info not equal to element? Yes, true. When both true, it will move temp. So temp is moved, temp points here. Again, temp is not null. Temp's info is not equal to element. We are searching for 30 but it is 20. Both conditions are true. Temp is moved. Temp will be here. Again, temp is not null. Yes, true. Temp's info is not equal to element. No, this is false now. It is equal to element to be searched. So when it comes out of this loop, our temp is pointing to the node to be deleted either, or temp might be null. Either temp is, if it is present, temp is pointing to that node definitely. If it is absent, temp will have null value. In any case, when it comes out of this, if you write return temp, that's it. It will return that node's address. We'll see. For 30, temp has stopped here. After a while, return temp means this node's address you are returning. If suppose you are searching for 50, what will happen? See, what will happen if 50? Is it 50? No, moved. 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 Moved means temp will be null. This condition will be false in that case. It will come out. It will come out of this loop. In that case also, what is temp's value? Temp is null. So null will be returned. Now when null is returned, what does it mean in find element? The element is not found. That here also it is returning null. The element is not there. Linked list is empty means element whatever you are searching is not there. And if element is not there, when you return temp, if it returns null, that means element is not there. We are assuming in caller, right? This is the way. How to find predecessor? That is also similar thing. Find predecessor of element. Find predecessor. What you are passing? Two addresses, struct node star, I'll say that element's address in PTR, and it is also giving you the predecessor node's address. What way I have to see? If start is null, again this case will be there definitely, because if linked list is empty and you are searching for a predecessor, then it gives. Now see, if special case, all cases will see what exactly you have to do here. if the address you are searching for is first node's address itself, if that first node's address starts this, if this start here, start is equal to PTR, what does it mean? That is, whatever starting node its address is PTR, this is start for function, and PTR is the first node. The address sent to this find predecessor is first node itself. Do we have predecessor for this? No. It should return me null, because there is no predecessor for first node. It should return null in that case, right? But if it is not that, if it is not the address of first node, if it is somewhere, so PTR is this, you have PTR as this, suppose. What you have to find predecessor node, this node's address. Keeping temp here, this keeping temp is given start. This else part I am writing. So start, this temp is pointing here, now. Then while. Now you have to find out predecessor of that PTR. When to stop? Temp is here. Check this node's address. Is it equal to PTR? Means this field. Is it equal to PTR? Next node is PTR. Temp is here. Temp's link is this node's address. Is it PTR? No. Move. Is link is pointing here, suppose. Is it PTR? Yes. So temp should stop here. When PTR is this, when element is there, then only you are sending that element's address, right? If element is not there, you are not sending this. If this will be null, if this start is equal to null, and or this PTR is also null. If PTR is also null, if this is null or this is null, in both the cases it cannot find predecessor. So return null directly you can do. But when you are finding the predecessor, this pointer will be definitely on one of the node. This PTR will point to either this or this. First node we have tackled. If first node we have tackled here. If it is not first node, for next nodes what you have to do, either pointer PTR maybe here, maybe here, maybe here. We have tackled this case here. So when it is there, we have predecessor node. That node you have to find out. So up to what you have to continue this. Definitely PTR is there, we know. So what condition we have to check? Keeping temp here, you have to check what is this node's address. Is it PTR? So what if temp's link not equal to null, PTR, whatever you are searching, temp link is this is not PTR, move temp is given temp's link field. That's it. It will stop to the predecessor node for definite. You take any PTR, its predecessor node, where it will stop. See, temp is here. Temp's link, is it PTR? No. Move. Temp's link, is it PTR? Yes. This will be equal. This PTR and this PTR, you have sent this PTR and this address. They are equal. Means temp is here and it is giving us predecessor node. After this, definitely you will get predecessor node's address. Directly you can say return temp. That's it. These two functions are over. Right? So this way you can write different functions and call that functions in other functions also. So give some, while writing in some programs I might be forgetting declaration of some pointers whatever we are using here. So here the special pointer that you are using is temp I have declared, but in some programs I might have not declared. So see that are minor errors that might be happening in my writing, but explanation, you should see the broad view how to do these operations. In writing sometimes I may miss. When you code these programs, then you will get errors and you have to tackle that. If variable is not there, what to do, and all cases should be given, test cases should be given whenever you are testing. So this is all about deletion of given element by normal one monolithic function we have seen, and by calling other functions into that delete given element function. So we'll stop here. Thank you.